Section: Introduction. In this section, we discuss the concept of agents in artificial intelligence, which has been debated for many years. Broadly, an agent is anything that can sense its environment and act upon it. As our daily tasks increasingly shift to digital platforms, developing computer agents that can perceive, plan, and act in these virtual spaces can significantly boost our productivity and software accessibility. We note that advanced multimodal models like GPT-4v and others are currently the foundation for agents tested in various benchmarks, particularly in areas like web navigation and software development. However, these benchmarks often fail to capture the complexity of real human workflows, where we frequently switch between different applications and interfaces to complete tasks. To bridge this gap, we introduce OS World and Android World as benchmarks that integrate real computer and mobile operating systems into the testing environment, aligning the observation and action spaces more closely with human computing experiences. Our contribution, WINDOWSAGENTARENA, builds on the OS World framework to enhance the development and testing of multimodal agents specifically within the Windows operating system, which is the most widely used OS among users and businesses. We offer a variety of tasks with automatic evaluation criteria that prioritize task completion over following pre-recorded human actions. WINDOWSAGENTARENA is designed to be scalable and can be deployed in secure Docker containers on Azure virtual machines. We recognize that agent evaluations can be slow due to the sequential nature of tasks, often taking days to complete. Instead of speeding up the simulation, we focus on parallelizing tasks to speed up evaluations. Additionally, we present a new agent for Windows, named Navi, which serves as a starting point for developers and researchers using our benchmark. We provide different versions of Navi for future reference. Our main contributions include the introduction of WINDOWSAGENTARENA, which features 154 diverse and realistic multi-step tasks for the Windows OS and allows for parallel deployment in Azure, reducing evaluation time to as little as 20 minutes. We also plan to continuously update WINDOWSAGENTARENA with new tasks and capabilities. Our new multimodal agent, Navi, has been benchmarked, achieving a 19.5% success rate using specific prompting techniques. We also tested Navi on another benchmark, Mind2Web, confirming its competitive performance. We are committed to making our code, benchmark, and models available as open-source resources for the research community, facilitating further agent development and faster experimentation in the Windows environment. In terms of prior work, we highlight the advancements in large language models, LLMs, and their potential as autonomous agents, particularly with improvements in multimodal capabilities. Various models have been tested in different environments, but many benchmarks rely on static datasets, which limit their ability to capture the full range of agent actions. In contrast, interactive benchmarks allow for more dynamic evaluations, enabling agents to utilize available tools in both predefined and open-ended environments. Our work builds upon existing benchmarks, particularly OS World, to focus on the Windows OS. Section Summary. In this section, we introduce WINDOWSAGENTARENA, a benchmark suite designed for evaluating multimodal agents specifically within the Windows OS ecosystem, featuring 154 diverse tasks that reflect realistic user workflows. Our approach emphasizes task parallelization for faster evaluations, and we also present a new agent, Navi, which serves as a foundation for future developments in agent performance testing. Section: Evaluation Scalability. In this section, we discuss the scalability of evaluation. A significant challenge that often goes unmentioned is the time required to evaluate benchmarks. Many referenced works involve tasks that take about 10 to 20 steps to complete. If each step takes 10 to 30 seconds using local models and cloud API calls, evaluating hundreds of tasks sequentially could take 1 or more days. Most studies do not directly tackle this issue. While OS World allows for some parallel simulations on a single machine, it is limited to a small number of agents due to memory and CPU limitations. We address this by offering native cloud parallelization, which can scale according to the number of benchmark tasks. Next, we define the task. We model agent behavior as a partially observable Markov decision process, which includes state space, observation space, action space, transition function, and reward function. Given the current observation, the agent generates an action that leads to a new state and observation. This process continues until the agent either completes the task or reaches a maximum number of steps. The reward function provides a non-zero value at the final step if the agent meets the task objective or correctly predicts failure for an impossible task. Depending on the task, the reward can be either binary or a decimal value based on how closely the outcome aligns with the objective. We note that the benchmark could be adjusted to allow for partial rewards during the evaluation, which we consider for future work. We then describe the observation space, which includes all the information available to the agent at each time step. This encompasses task instructions, clipboard content, session metadata, and a representation of the current screen. The screen can be represented in various formats, such as screenshots or UI trees. For each task, we use a script to set the initial system state, which may involve opening applications or navigating to web pages. Regarding the action space, we provide two types: free-form code execution and function wrappers through the computer class. This class allows the agent to perform OS-related functions with high precision and interact with screen elements directly. For reward evaluation, we follow OS World guidelines and use scripts to assess task completion. This may involve checking system states, file contents, or using web functions to evaluate results. In terms of task curation for Windows OS, our initial release of WindowsAgentArena includes 154 diverse tasks that reflect typical user activities on Windows, such as document editing, web browsing, and coding. Each task is defined by a configuration file that includes instructions, setup steps, evaluation criteria, and the evaluation method. We adapted about 2/3 of these tasks from Osworld's Linux configurations, making necessary adjustments for Windows compatibility. The remaining tasks were created from scratch to cover a broader range of Windows-specific applications. Human performance on WINDOWSAGENTARENA shows a 74.5% success rate, with the highest success rate in Windows Utilities tasks and the lowest in VLC player tasks. We provide further details and analysis on success rates and task difficulty in the appendix. Section Summary. In this section, we discuss the challenges of evaluation scalability in benchmark tasks, highlighting that traditional methods can take days to complete due to sequential processing limitations. We introduce a cloud parallelization approach to enhance scalability, formalize agent behavior using a partially observable Markov decision process, POMDP, and outline the task and observation spaces, action types, and reward evaluation methods, while also detailing the diverse tasks included in our WINDOWSAGENTARENA benchmark. Section: Deployment Infrastructure. In this section, we describe the infrastructure we created for WINDOWSAGENTARENA, which allows for flexible local execution and scalable, secure cloud parallelization using Azure. Our system is built around a Docker container that runs a Windows 11 virtual machine, VM. Inside this container, we set up a client process for scheduling tasks and configuring the system, along with the agent and evaluation scripts. The VM serves as our main simulation environment, where a Python Flask server connects the container and the VM by receiving commands from the client, executing them in the VM, and sending back observations and files. Due to licensing issues, we cannot provide a pre-built Windows 11 snapshot, but we offer open-source instructions for users to download a trial image from Microsoft and use our scripts to prepare it for benchmarking. We deploy the VM using QEMU and KVM, based on a process adapted from the Docker, Windows Docker image. For local runs, we can use either Ubuntu or Windows Subsystem for Linux, WSL. To streamline the process, we avoid frequent rebuilding of the Docker image by mounting external volumes with the OS image and code from the user's machine onto the container. In the cloud, we utilize Azure Machine Learning jobs to parallelize benchmark evaluations with compute instances. This setup is similar to local deployment, but VMs are created and destroyed with each experiment submission. We manage the Windows 11 snapshot and output logs using Azure Blob Store, while the code is pre-configured in the Docker image. Tasks are evenly distributed among workers, and results are compiled at the end of the run. We provide more information on VM types in the appendix. Our approach differs from OS World, which uses multiple VMware VMs on a single local host. We believe our method is more scalable, as it allows for a number of workers equal to the number of tasks, leading to faster evaluations. We discuss parallel evaluation runtimes in the appendix. Regarding security, we ensure that the agent and Windows VM control ports are not exposed to the Internet by using isolated compute instances with Docker containers. This setup minimizes risks related to data or code leakage. Next, we present the implementation details and results of our agent, Navi, within WINDOWSAGENTARENA, along with an analysis of its strengths and weaknesses. Navi is a new multimodal agent designed to operate autonomously in the Windows environment. We employ chain-of-thought prompting to guide the agent in reasoning about the computer's current state, its past actions, and determining the best next action. Navi receives input that includes the title of the active window, titles of other open windows or browser tabs, and a representation of the current screen. We explore various methods for processing the screen representation to create set of marks, SOMs, including UIA tree parsing, DOM tree parsing, OCR, icon and image detection, and a proprietary model called Omni Parser that detects text, icons, and images. During deployment, we test configurations that combine pixel-based segmentation with UIA tree information for a more detailed screen representation. Our code repository includes an open-sourced version of Navi that uses only open-source models for SOM generation. The full prompt to the agent includes task instructions, a description of the action space, a history of previous actions, clipboard content, and a memory block for storing variables or thoughts. We provide the agent with an annotated image containing SOMs and a screenshot of the previous state. The agent first answers questions related to screen understanding and long-term task planning before generating the Python code for the next action. More details can be found in the appendix. Section Summary. In this section, we describe the deployment infrastructure for WINDOWSAGENTARENA, which utilizes Docker containers and Azure for flexible local execution and scalable cloud parallelization, ensuring secure communication and efficient task distribution. We also introduce our multimodal agent, Navi, designed for autonomous operation within the Windows environment, employing various methods for screen representation and decision-making based on the current state and past actions. Section WINDOWSAGENTARENA Baseline Results. In this section, we summarize the baseline results from WINDOWSAGENTARENA, comparing different variants of Navi that use various set of marks, SOM, and reasoning models. We present an example of a successful task using proprietary models, with additional examples available in the appendix. Here are some key insights we observed. First, generalist zero-shot visual language model, VLM, agents still lag behind human performance. Our best agent, which combines UIA with OmniParser and GPT-4 v1106, only achieves a success rate of 19.5%, while humans perform at 74.5%. The performance varies by task. The agent is better with text-heavy interfaces like web browsers and worse with tasks that depend on keyboard shortcuts and icons, such as Office applications. However, Navi's results are comparable to similar benchmarks like OS World and Android World. Second, precise set of marks are essential for agent performance. We found that the quality of visual prompting significantly affects outcomes. When SOM bounding boxes are imprecise, the agent often selects the wrong elements. Adding high-quality UIA markers improves performance significantly, by 57% for omniparser, 52% for open-source models, and 15% for proprietary pixel models when using GPT-4v1106. However, querying UIA markers can take from a few seconds to several minutes, depending on screen complexity. Third, visual language misalignment frequently leads to failures. We observed that agents often struggle to align their text outputs with their visual understanding. For instance, an agent might correctly describe an action but fail to select the right visual element due to a mismatch between the training data and the tasks, which often involve many small markers. We believe Omniparser's superior performance is partly due to its ability to caption icons, linking visual IDs with text descriptions effectively. Lastly, we noted a significant performance gap between base models. GPT-4v1106 outperforms Phi-3v, GPT-4o Mini, and GPT-4o in most categories, achieving more than double the success rate of GPT-4o when using UIA and Omniparser. Smaller models like Phi-3v and GPT-4o Mini generally perform worse, and Phi-3v tends to hallucinate when planning multiple steps or dealing with long inputs. We also evaluated Navi on the Mind 2 web benchmark to assess its performance and robustness in a different context. Navi achieved state-of-the-art results compared to the original CACT agent. We found that combining image and DOM-SOM prompting yields the best performance, similar to our findings in WINDOWSAGENTARENA. More details on our evaluation setup can be found in the appendix.